Swayam Prabha. Digital India. Educated India.
Welcome to the 18th lecture in our particle characterization course. In the last lecture, we discussed ways of measuring the adhesion force of single particles as well as assemblies of particles on surfaces. And the key point there is adhesion force is typically measured indirectly by measuring the force that is required to remove particles from a surface. Now, in order to be able to remove particles from a surface, again in a repeatable and reproducible way, we need to have a good characterization of particle removal methods from surfaces. And as I was mentioning in the last lecture, such particle removal methods can be classified as being dry and wet methods, depending on whether we use a liquid medium to enhance the removal process or not. Another way of classifying particle removal processes is by looking at the mechanism involved. Particles can essentially be removed from surfaces using three different mechanisms. One is simple mechanical action, which includes vibratory action. The second is shear and drag based mechanisms, where you actually exert a parallel or tangential force to the particle sitting on a surface and dislodge it from the surface. And the third method is simply chemical cleaning or chemical removal of particles, where you use a fairly strong chemistry to dissolve the particle on the surface and entrain it into the chemical medium. And there are various combinations of these. So, we talked about dry methods of particle removal and wet methods of particle removal. This is based on the medium that is used. Based on the mechanism, the classifications are mechanical / vibratory, shear / drag, the third is chemical methods of particle removal. Now, if you take various combinations of these, for example, a dry process that involves mechanical methods of particle removal. A classic example of this is brushing or scrubbing, right. So, if you see some dirt on a surface, you can basically take a scrub or a brush and just run it over the surface until the contamination that you see is removed. Brushing is a process that essentially uses an abrasive mechanism. You bring one solid surface in contact with another solid surface and impart a motion that essentially abrades any material that is sitting on the surface. It's a very aggressive process. It's a line of sight process. Obviously, you have to see the contaminant in order to be able to remove it. So, if you have any hidden recesses or features in your part, this method is not going to be able to effectively dislodge particles that are located in such places. It can be automated. In fact, in many process industries, you essentially do double-sided brush cleaning. So, for example, if you have a rotationally symmetric part, you can mount it on a device, rotate it at high speed while one brush goes on top and one brush goes on the bottom, and this is very effective in removing simultaneously particles that are adhered on the top surface and particles that are adhered on the bottom surface. The downside of brushing as a cleaning process is that it is very aggressive. It is very easy to damage delicate surfaces when the bristles of a brush come in contact with it, because when you are trying to remove contaminants from a surface, it is very difficult to control that process so precisely that the brush only contacts the particles sitting on the surface. It is just as likely that it will contact the substrate itself at locations where there are no particles, and when it does, it can cause quite severe physical damage to the substrate. So this kind of brush cleaning or scrub cleaning in dry mode involves a lot of potential for surface damage, so it has to be carefully managed. Now an alternative to this is the wet mechanical process, which again is brushing or scrubbing, but now you do it in the presence of a liquid. So for example, you could take a brush and run the same process I was describing earlier. Let us say you have a substrate that is rotating and you run the brush on top of it, but now you actually introduce a liquid like water as an intervening medium. Now what happens? Actually the brush, when there is a liquid in between, never physically contacts the surface. Instead what happens is what we call hydroplaning. The viscosity of the intervening liquid layer is high enough that it prevents the bristles from contacting the surface itself. So the solid brush tips stay essentially a few micrometers above the substrate surface that is being cleaned, and the liquid acts like a buffer and prevents actual physical contact between the particle and the surface, but at the same time it allows contact between the surface contaminants and the brush material. And so by taking advantage of this hydroplaning action, you can remove particles while at the same time not causing damage to the surface. And here again it is important that the liquid be able to wet the interface between the particle and the surface. If not, if you have a highly hydrophobic surface for example, this process will not work. So here again typically what is done is to use a little bit of surfactant. The surfactant enables the surface tension of the liquid to be reduced, so it wets the capillary region better and it makes this hydroplaning removal process that much more effective. So either by using a water alone or some polar solvent, or by using an organic solvent, or by using water in combination with a surfactant or detergent, you can effectively brush particles away from a surface without causing excessive damage to the surface. Now let us come back to dry mechanical processes. Another process that we can imagine is wiping. So again you can imagine, I am sure you have done this many times, you see something, let us say on a surface, you just take a dry cloth and wipe it and it removes the material that is there. Now dry wiping is a process that is again widely used in many manufacturing industries to remove visible dirt, and in fact it enables us to also monitor cleanliness at the same time. If you take a very white cloth and you rub it on a surface, if there is any dirt there, it changes color, right? You can see the accumulation of dirt on this white surface. So basically you just keep taking fresh wipes and keep repeating the process until nothing transfers to the wipe. So you can actually achieve endpoint control using this dry wipe process. In fact there is a test in, for example, clean room manufacturing called the white glove test. Essentially you wear a white glove and just touch a surface and rub your finger if you can see something on the glove, that means it's dirty. So you essentially keep cleaning the surface until when you do the white glove test, nothing transfers to your white glove. So dry wiping is a method that simultaneously removes contamination and can also be used as at least a visual check of how clean a surface is. And here again, just like in this case, in addition to doing this in a dry mode, you can also do a wet wipe. Now in a wet wipe, all you do is take the wipe cloth and soak it in some liquid. It could be water if you are just trying to remove hydrophilic material from a surface, or it could be a solvent if you are trying to remove hydrophobic or hydrocarbon material from a surface. And wet wiping has the inbuilt advantage that again it can reach particles that are hard to reach with a dry wipe. The other problem with the dry wiping process is again there can be damage. When you wipe a surface with a wipe cloth, the surface can damage the cloth and actually generate fragments of the cloth material, which can become a particle contaminant. In a wet wipe, essentially you avoid that to a large extent, because again when you soak the wipe, the contact between the wipe and the surface is not as stiff as when you have a dry wipe. So the potential for damaging the wipe is lower when you have a wet wiping process. Plus the fact that you can wet it with different chemicals, different solvents, different chemistries, means that you can, in addition to simply removing particles from by a physical mechanism, you can also now chemically remove material from the surface. For example, if you have oil on a table, or you have these stains on the table, if I just try to remove it with a dry wipe, probably won't work, or a dry brush, it won't work. But if I know that it's something oily, then if I take a wipe and soak it with some detergent and then do the wiping, it will remove the spot, right. So that's the difference between a wet wipe and a dry wipe. Dry wiping works okay when all you have to worry about is loose dirt that has accumulated on the surface just because of room debris depositing on the surface. But if there is a possibility that you can have an oily layer or a hydrophobic layer or something that is like a film on the surface rather than being dry particulates, then you are better off using a wet scrub or a wet wipe process. Another mechanism of dry removal using mechanical means is vacuuming. I am sure you have all seen the use of vacuum to clean houses, automobiles, and the way it works is essentially you take a tip through which you pull vacuum and you take the tip as close to the surface that you want to clean as possible, and it just sucks up the dirt from the surface, right. Here again I am sure you have seen there is dry vac and there is also wet vacuum. In a wet vacuum process, you initially soak the surface. For example, if you are trying to clean carpet, a wet vacuum process works better because initially you deposit a cleaning chemical on the surface, let it dry, and as it does it converts the contaminants into loose flakes of material on the surface, and then you follow it up with a dry vacuum. So vacuuming has huge advantages because it's an in situ process. In other words, if I'm running a manufacturing process here and I see some contaminants and this is my workstation, then I can just take a vacuum wand and just pull off the material right here. If I have to do a wet cleaning, I have to take it out of the clean room, clean it, dry it, and then bring it back in. So vacuuming has a lot of advantages in terms of convenience, can be localized. So you can there are what are known as gang vacuums, where you essentially have multiple vacuum tubes and you can use them to pull off material wherever you see it. So instead of applying your vacuum over the entire surface, you can apply the vacuum in a very localized fashion. So that makes it possible to remove particles from surfaces in a way where you don't have to worry about again damaging certain materials by pulling vacuum. As an example, if you have a motor and it's filled with some lubricant or grease, you apply vacuum to it to remove dirt. It can also pull off the lube, right, which you don't want to do. You want to leave the grease intact and only remove the particle dirt that you see. In that case, you are better off using this localized vacuum tips that can just pull off material from wherever you want to do the cleaning and leave the rest of the surface undisturbed. So, so dry vacuuming is a good option. The downside of vacuuming is that it's only really good for removing large particles. If you look at the force of vacuum, for the kind of vacuum that you can normally achieve, it is typically not enough to overcome the adhesion force of very, very fine particles. So, vacuuming is good to remove particles that you can see usually. It removes visible dirt very well, but it is not very effective in removing finer dirt. The other problem is that if you do not control the distance between the tip and the surface carefully, the tip can actually hit the surface and thereby generate particles. And so, this requires a high degree of mechanization, automation, precision control, all of which can increase the cost of the process quite significantly. So, vacuuming, you know, by definition is a simple process, but it is not that easy to implement it in high volume manufacturing, because unless you have perfect controls over the process, again you may be removing visible dirt, but you may be creating or generating 1,000 times as many fine particles. That is a penalty you pay when you are using a purely vacuum based particle removal process. Now, there are other methods that are somewhat more esoteric. For example, you can think about using a tape cleaning. You can, if you see some dirt, a simple way to remove the dirt is to take an adhesive tape, stick it on the surface and then peel off the tape. It will peel off the dirt also, right. Couple of issues with that. The tape itself has some adhesive material, and in the process of removing the particle, you can transfer that adhesive to the surface and thereby contaminate it with this hydrocarbon material while you are removing particles that are there. And the other problem with the tape cleaning is that it only works for very smooth and polished surfaces. If you have a rough surface where particles can hide in the roughness asperities, tape cleaning would not work. However, there are some interesting applications of tape cleaning technology. Polyvinyl acetate is an interesting material. You can essentially lay it down as a liquid on a surface, it will solidify and form a film, and then you can just peel off the film. So, this PVA film cleaning is used quite extensively, again in high technology manufacturing industries, to remove particles from surfaces where other techniques do not work. Another method of dry cleaning is simple abrasive cleaning. Now, this usually works when you are trying to remove gross material from a surface. For example, if you have a machined part and there are burrs hanging from the surface, then blasting it with an abrasive will remove these burrs that are hanging from the surface. So, abrasive cleaning is a process that is extremely aggressive. You are taking material that has high mass and kinetic energy and impacting the surface with it, which will essentially transfer that kinetic energy to whatever it impacts upon, and it will knock off material from the surface. But here again, the potential for doing damage is quite high if you are not controlling the kinetic energy of the impacting material and its direction. You can quite easily cause unanticipated damage to the substrate you are cleaning. But for processes like deburring, even paint removal, frequently you have applications where you have to remove paint from a surface and then reapply a surface coating. Abrasives are used for things like paint removal, which is virtually impossible to achieve by any other means. Quite widely used, for example, in the aircraft industry, where the wings of the plane have to be frequently repainted. And so, the only large scale process that will enable us to do that is deburring using abrasive blasting. Other dry processes for particle removal that are used, again going back to dry mechanical, laser cleaning. It turns out that if you train a laser on a surface, you can actually knock off particles that are on the surface. There's two ways in which this can happen. When the laser hits the surface, if it happens to hit exactly where the particle is, just the energy transfer alone may be sufficient to knock off the particle. But even otherwise, when you train a laser on a surface, you essentially increase its state of excitation. You set up a microscopic vibration of the surface simply by increasing its thermal energy. And as you do that, the particle that's sitting on the surface, when the surface itself starts oscillating, a particle that was initially sitting on the surface is now also oscillating on the surface. So if you do the laser entrainment and have some gas flow at fairly high velocities over the surface, it can actually entrain these particles and transport them away. So laser cleaning is again widely used when you have very localized contamination that you want to remove, and the surface is such that you cannot expose it to water or any other chemical. Laser cleaning gives you a way to do this particle removal very precisely and completely. Laser cleaning can also be done in a wet mode. Here what you do is you soak the surface in a solvent. For example, let's say you soak it in methanol, and then you train the laser on it before the methanol has evaporated. Then what happens? The laser energy actually causes that solvent to evaporate in an explosive way. It essentially just boils the solvent off the surface. And as it does, once again, the particles that are entrained now in the liquid or the solvent that the surface has been immersed in are removed from the surface, not just by the vibratory action of the surface, but because of this explosive boiling of the solvent that has been placed on the surface. So particle removal efficiency using laser can be enhanced by a factor of 10 or higher simply by pre-soaking the surface in a highly volatile solvent. It really doesn't work very well if you use water as the medium, because water takes a lot of energy to vaporize. But if you take a solvent like methanol that has high volatility anyway, all it takes is a little bit of laser energy to cause it to evaporate from the surface, and as it does, it takes a particle with it. Another dry cleaning action which does not involve liquids is what's known as CO2 snow cleaning. CO2 snow refers to the conversion of either gaseous or liquid carbon dioxide to a form where it looks like snowflakes. So essentially by taking the source supply and expanding it through the nozzle and cooling it, you can convert it to very, very fine particles. In fact, you can control the size of the particles that you create out of these nozzles. If you create very, very fine CO2 particles, this is called snow. If you create larger particles, this is called pellet. And if you expand it in such a way that it reaches a supercritical region where it has properties of both a liquid and a gas, then that's called supercritical carbon dioxide. So simply by controlling your expansion process, by controlling the design of the nozzle, you can feed in liquid or gaseous CO2 and produce either snow, CO2 snow, which is very, very fine flakes of carbon dioxide, or CO2 pellets, which are larger sized solid carbon dioxide, or a fluid supercritical CO2, which has essentially the density of a liquid but the diffusivity of a gas. So from a particle removal viewpoint, it combines the best aspects of both liquid carbon dioxide as well as gaseous carbon dioxide. And by the way, if you liquefy it, you can certainly produce liquid CO2. Now CO2 is an excellent solvent for many reasons. One is that it works very well in terms of reacting with hydrocarbons and dissolving them. Also, this conversion of CO2 to various forms can be done pretty much close to atmospheric conditions. You do not have to go to extremely low pressures or high pressures or extremely high temperatures in order for these conversions to happen. Now, when you take CO2 that has been converted, for example, to liquid CO2, then that becomes a wet cleaning process. Liquid carbon dioxide is an excellent solvent. So, you can take any material that has, again, visible hydrocarbons on it like oils, you expose it to liquid carbon dioxide, it will completely remove the hydrocarbon material. Supercritical CO2 has the ability to remove materials selectively. So, you can actually tune it to remove the contaminant that you are looking for. Again, by controlling the conditions of expansion, you can produce supercritical CO2 with very different solvency properties and make it particularly effective for certain types of contaminants. So, if you know what the nature of the oil is on your surface, you can produce a supercritical carbon dioxide which is specifically optimized to remove that particular oil. So, this is kind of somewhere between a wet process and a dry process. It is not liquid CO2, so you really cannot call it a wet process, but at the same time it is not a fully dry process. So, it kind of falls in the region between wet and dry cleaning. CO2 pellet cleaning is somewhat like the abrasive blasting that we talked about earlier. So, instead of using abrasives like alumina or silica to do your blasting, deburring and so on, you take carbon dioxide pellets and do it. Now, the advantage of carbon dioxide pellet cleaning is it does not cause surface damage to the same extent. The hardness, the abrasiveness of carbon dioxide is much lower compared to commercial abrasives that you might use otherwise, and also